Okay, so now we'll welcome the last speaker for this session, who is Catherine Walsh, and she'll be speaking about integrating multimodal neuroimaging features to predict working memory and psychiatric disability.
Hi everyone, thanks so much for sticking around to this end of the session. My name is Catherine and I'm really excited to be telling you about some of my work trying to predict working memory and psychiatric disability. So to start, I want to give you a little bit of background on why we should focus on working memory capacity. We know that working memory capacity is positively correlated with other higher order cognitive ability. So for instance, fluid intelligence, reasoning ability, and procedural and declarative learning. On the other hand, we also know that working memory capacity is negatively correlated with psychiatric dysfunction across different psychiatric conditions. For instance, in schizophrenia, anxiety, depression, and autism spectrum disorder. That said, in many of these studies that look at this, they only look at one psychiatric population at a time. So kind of with that framework in mind, I'm going to try to answer two questions today. First, what neuroimaging features can predict individual differences in working memory capacity and working memory performance? And second, can those features that can predict individual differences in working memory capacity also be used to predict transdiagnostic psychiatric disability? So to answer those questions, so to that end, we collected a large heterogeneous sample in a Research Domain Criteria inspired framework. So that is to say, we collected participants who were either care-seeking or non-care seeking. Our care-seeking participant group was comprised of individuals who were seeking treatment for psychiatric or emotional distress. Our non-care seeking group was just normal, healthy volunteers. Our care-seeking group, however, was not restricted to any one single DSM diagnosis, so it gave us a wide variety of psychiatric symptomatology. For all of our analyses, we collapsed across these two groups to have a larger sample of 169 usable participants. Each participant completed a wide battery of behavioral testing, which indexed working memory, long-term memory, and intelligence, in addition to self-reported clinical symptomatology. Finally, we had a neuroimaging session, which included resting state fMRI, a delayed face recognition task, which I'll tell you about in just a moment, and structural MRI. And I just want to note that all this data is available on the NIH Data Archive. So now I want to tell you about the behavioral measures that we were trying to predict. I already mentioned that participants completed a delayed face recognition task. This task was a delayed match to sample task where participants were asked to encode either 3 faces, which I'm showing here, or 1 face. After a short 7.5-second delay, participants were given a probe face where they had to decide whether that face matched the face they encoded earlier, and in between trials they had an active baseline. In addition to this measure of task performance that was happening in the scanner, we also wanted to have a measure of more general working memory capacity. So we turned to our data from the cognitive task battery that I mentioned before, and we conducted an exploratory factor analysis. So here I'm showing you 4 tasks, but we did this on our whole 10-task battery. Our exploratory factor analysis resulted with 2 factors that comprised of visual and verbal working memory capacity. Finally, we wanted to predict a measure of overall psychiatric functioning, so we turned to the World Health Organization Disability Assessment Scale, which I'll refer to as the WHODAS. So today I'm going to show you models predicting the overall DFR task performance, visual working memory capacity, and WHODAS scores. So now I've gone over some outcome measures. I want to talk about the features that we use to try to predict these measures. We can break those down into structural brain measures, which we can further break down into cortical, subcortical measures, in addition to structural connectivity. More specifically, we extracted cortical volume, cortical surface area, and cortical thickness, subcortical volume, and DTI measures. We had the mean FA from various tracks from Alice. Additionally, we calculated a number of functional measures taken from both resting state and our stand DFR task. For resting state, we had average within and across network functional connectivity and measures of graph theoretical measures of network structure. From task measures, we calculated traditional univariate GLM load effects from the encoding, delay, and probe period, 2 measures of pattern similarity, which encompass the content representation during the delay period and overall encoding to delay similarity, and beta series task connectivity from the encoding, delay, and probe period. So we have a lot of measures, and we needed to try to find a way to integrate all those measures. To that end, we used stacked models, a 2-step ensemble machine learning modeling procedure. To show you how that worked, I'm going to give you a toy example. So at our first layer of models, for which we used ElasticNet, it was pretty much a standard machine learning prediction analysis. We could take any one of our set of measures, so for instance here, the univariate GLM from the delay period, and extract different regions for each of our RIs for each person. These served as our features for these models. We could train our ElasticNet model and get predicted values for any behavioral scores, so here, the predicted working memory capacity. So we did this for one measure, and then we did this for all of our measures. So for instance, we could do it for cortical thickness, subcortical volume, and resting state functional connectivity. Again, here I'm only showing you 4 examples, but we did this for all 17 of our different neuroimaging features. Once we finished all of these, which I'm going to call our layer 1 models, we start constructing our layer 2 models, for which we used lasso regression. In this model, we take the predicted working memory capacity scores, or any behavioral score for each of the models, and used those as our features for the second level model. We then trained a lasso regression model to get an aggregate layer 2 prediction for our behavioral outcomes. Now, I've shown you the training of these models, and in order to test how well our model generalized, we took our trained models and applied them to a set of held-out test data. We did this whole modeling procedure in a 10-fold cross-validation framework, which we repeated 10 times. So we had 2 goals for these stacked models. First, a relatively basic one, we wanted to predict behavioral outcomes from our neuroimaging measures. Using our stacked models, we were able to get a predicted value for each participant, which we then concatenated across all of our 10 folds to create one single vector of predicted scores, which we then correlated to the true working memory scores to get an index of how well our model was doing. We measured statistical significance of these models by comparing to a permuted null distribution. So our second goal for these models was to try to interpret the influence of our neuroimaging measure on prediction. Put another way, we wanted to be able to answer questions about whether one individual class of features, so for instance, the univariate activation, was more important than another, like cortical thickness, rather than try to understand the influence of any individual pair of ROIs. So to accomplish this, we looked deeper into our layer 2 models, where we extracted the lasso weights from each models and used those as a measure of influence for each neuroimaging measure on predicting behavioral outcomes. So let's turn to our first research question. So I'm going to start by showing you the results from predicting the DFR task performance. To orient you, the first thing I'm going to show you is a box plot of the Pearson correlations across the 10 repetitions of our modeling. We were able to predict DFR task performance with a median Pearson correlation of about 0.46. So we're doing quite well. So next I want to show you the important neuroimaging features in predicting our model. So here I'm going to show you the lasso coefficients across our cross-validation folds, where a larger value here indicates a more important feature. So here, I want to highlight a few things. First, almost all of the features that were retained and statistically significant in these models were from our scanned DFR task. And this is kind of intuitive. What you're doing during a task is predictive of how well you do on that task. However, there are a couple of things I also want to point out. Our most important features in this model were our multivariate features, one being task connectivity and one being a measure of pattern similarity, whereas our univariate GLM contrast from the delay period, which are often used to study working memory, was our least important significant feature in this model. So moving on to our predicting visual working memory capacity. Although these models were predicted less accurately than our models predicting DFR task performance, we were still able to significantly predict visual working memory capacity with a median Pearson correlation of 0.22. So if we look at the lasso weights for these models, we can first see that the measures of the scanned DFR task are also important in predicting visual working memory. However, it's also important to note that unlike in the model predicting DFR task performance, many other more trait-like measures, so for instance, structural connectivity and resting state network structure or network connectivity, are also predictive of these features. So I've just shown you that there are some differences across these models, but in general, there is a wide variety of features that can predict this. So now I want to show whether these same features can also be used to predict transdiagnostic psychiatric disability. So if we go back to our final model trying to predict our HDAS score, it was our weakest predictive ability, but we still were able to significantly predict HDAS scores with a median Pearson correlation of about 0.14. If we look at the lasso weights from this model, we can see some divergence from the working memory models. For instance, we can see that the most important features in the model are more structural, more trait-like measures. However, we also do see that measures from our working memory task are also significant predictors of our HUDAS scores. So to close out this talk, I want to reiterate some takeaways from this work. First, stacked models are a promising analytic framework that leverages numerous aspects of brain structure and function to predict individual differences in working memory performance and capacity. Using these models, I have shown you that there's a diverse set of functional imaging features from a scanned working memory task are predictive of individual differences in both performance and capacity, and this includes not just univariate GLM contrasts, which have been traditionally used to study working memory in the past. I've also shown you that despite the correlation between working memory capacity and task performance, relatively distinct collection of features predict the two outcome measures. Finally, I've shown you that measures from a scanned working memory task are retained in models predicting indices of psychiatric disability, suggesting their potential utility as clinical biomarkers. And some of our future work will examine the specific predictive ability for specific psychiatric symptom classes. Thank you so much for listening. I want to acknowledge the great team that helped me collect this data and do this work. I've already given my poster, but I'm happy to touch base after or on various social media. So thank you so much.
Thank you, Catherine. We've got time for one very, very quick question, if there is one from the audience. I might ask a very quick question then. Did you test for differences between the care versus non-care seeking groups?
We did. So there were differences in some, but not the other. The status is. Psychiatric disability is negatively correlated with working memory capacity, which is what we expected. That said, we did want to leverage most of our analyses did focus on collapsing across groups because we really did want to have that wide heterogeneous kind of sample, the variability, so that we can actually accurately predict. So we did focus mostly on these kind of more continuous measures, but yeah.
Okay, thanks very much. And that's the end of the session. Thank you, everybody, for joining us.